All right, welcome back. This time we're going to go over recurrent neural networks, also known as RNNs. Before we get started, hit the like button, subscribe, and share with anyone you know taking the AWS Machine Learning exam. Recurrent neural networks. These are designed specifically for sequential data. Unlike feed-forward networks that treat each input independently, RNNs retain memory of prior inputs, allowing them to model patterns across time. This temporal awareness makes them essential for time series forecasting, natural language processing, audio generation, video captioning, and predictive maintenance. RNNs process inputs step by step, maintaining an internal state that evolves with each new time step. This memory enables them to remember previous information, making them effective at tasks involving temporal dynamics or ordered data where context matters. So, how do you apply this? Here we go. Time series forecasting. All right, so RNNs excel when context and sequence are critical. In time series prediction, they can forecast stuff like stock prices, sensor data, website traffic, or here we go, time series casting, right? So, how does it do this? By learning temporal patterns. Language modeling uses RNNs to predict the next word in a sentence based on prior words. Machine translation relies on RNNs to translate entire sentences while maintaining grammatical structure across languages. Sentiment analysis determines emotional tone by processing text sequentially. Music generation composes new notes based on existing melodies. Video captioning generates text descriptions by processing frame sequences. Self-driving vehicles model prior trajectories to predict next movements. So, how do they maintain memory? An RNN neuron contains a feedback loop that feeds outputs from the previous time step back into itself. When visualized over multiple time steps, this creates a chain where each output depends on both the current input and the previous hidden state. At time step 0, the network receives an input and produces the hidden state. At time step 1, it receives the input plus the previous hidden state to produce the next. This continues through the sequence, with each step incorporating information from all previous steps. However, this architecture has limitations. Older outputs have diminishing influence as the sequence lengthens. Information from the beginning of a long sentence might fade before reaching the end, causing problems when early context is critical. So, some architecture about this. A vanilla RNN uses a basic recurrent unit but suffers from vanishing gradients over long sequences, limiting its memory capacity. This makes it unsuitable for many real-world applications requiring long-term dependencies. LSTM, so that long short-term memory, these networks address this limitation by maintaining both long-term and short-term state through a system of gates. They excel at remembering dependencies across extended sequences, making them the standard choice for NLP tasks. LSTMs are available as built-in layers in TensorFlow and Keras. GRU, or gated recurrent units, these are networks that simplify the LSTM architecture while maintaining comparable performance. They can train faster due to fewer parameters and provide a good compromise between complexity and effectiveness. When computational resources are constrained, GRUs often match LSTM performance at lower costs. So, RNNs support various input-output patterns. Sequence to sequence, mapping predicts stock-based prices on historical patterns. Sequence to vector, mapping performs sentiment analysis on entire sentences, outputting a single classification. Vector to sequence mapping generates captions from a single image. Sequence to sequence with different lengths enables machine translation, converting French sentences to English sentences of potentially different lengths. This versatility allows RNNs to combine into encoder-decoder architectures that transform one sequence into another, the foundation of modern machine translation systems. So, here's some challenges with this. Training an RNN is significantly more complex than training a CNN or a standard neural network. So backpropagation through time, or BPTT, calculates gradients across time steps rather than just layers, exponentially increasing computational requirements. To manage this, truncated BPTT limits backpropagation to a window of recent time steps. So vanishing and exploding gradients plague RNN training on long sequences. Gradients can either decay to nothing or grow uncontrollably as they propagate backward through time. LSTM and GRU architectures specifically address these gradient problems through their gating mechanisms. So these RNNs, they're sensitive to hyperparameters. This means the sequence length, the learning rate, and the architecture. These heavily impact your training successes. And they also consume more memory and computation time than feed-forward networks due to their iterative nature and their need to maintain hidden states. So what does AWS work with this? All right. So AWS doesn't expose RNNs directly through the API, right? But they power several services behind the scenes. So Amazon Comprehend will use an RNN-derived NLP model internally for text analysis. Amazon Transcribe relies on RNN-like architectures for speech-to-text conversion. Amazon Poly uses sequence-based modeling for text-to-speech synthesis. So it generates natural-sounding speech by modeling temporal dependencies in audio. For custom RNN applications, you can go to SageMaker Studio, you can go to training jobs, and you can use TensorFlow and PyTorch to build and deploy your own LSTM or GRU models. You can even develop sequence models for your specific use cases. You can train them on SageMaker's GPUs and deploy them to endpoints for real-time predictions. All right. So for the exam, remember these essentials. When questions ask about sequential data processing, maintaining temporal context, or choosing architectures for time series or NLP tasks, RNNs, especially LSTM variants, are your answer. So thank you for joining. We're going to get going. Before we do, hit the like button, subscribe, and share with anyone you know taking the AWS Machine Learning Associate exam. Until then, have a good day.